Hello everyone, welcome to Physics Rocks It's True, and in this one we're looking at AS Theory Paper 3B. That's the practical theory section. We're going to take a look at this by doing the 2018 paper. We'll run through it and pick up the general themes and skills that you need to as we go through. So let's get into it. Okay, so this episode was billed to my class anyway as being a live stream. Unfortunately, I'm going to be a little bit indisposed at the time that we arranged, so this is a pre-record, but I will be available live at about 9 o'clock this evening. That's the 6th of May, in order to answer any questions. So if you've got questions about this, you've got things that you want to do, please leave a comment below this video so I can have a look at it as my day goes on. I'm going to be out and about, but I'll have my phone on me, so leave a comment, and that way any questions you've got, I can address those later on in the live stream. Alright, off we go then. Question 1. An experiment is carried out to investigate how the resistance of a piece of wire varies as the cross-section area of the wire is altered. The results from the experiment are shown in the table below. Okay, so we've got resistance, and immediately I'm having a pick up. I haven't looked at the rest of the paper yet, okay, so we're taking, like you, immediately I'm picking up this microamps here going on, and my cross-section area is a millimeters squared. Okay, these are non-standard units, so if I have to do a calculation later, I'm going to have to deal with that. Right, so we've got everything sorted out here. We're looking like we're dealing with a couple of significant figures. Gets a bit weird down here. So 3 decimal places across the top, 2 decimal places across the bottom. On figure 1.1, plot a graph. Okay, so we're going to have to plot a graph first. So we're going to flick to that. There's my graph page, and I've copied across the little table. Okay, we've got a graph page. And then after that, we go on to question 2. So there's no follow-up question from this. This is just a question 1. Kind of easy starter. Get yourself 8 marks for a graph. Right, so 8 marks for a graph, where are they coming from? First thing to do is to work out what my scaling is going to be. Now I've been asked to plot resistance against cross-sectional area. So when you're asked for something against something else, it's always y against x. So we should know now that resistance has to be on my y-axis against cross-sectional area, which is going to be on my x-axis. Okay, so it's always y against x. So we want resistance on the y-axis, cross-sectional area on the x-axis. There's always certainly a mark for that. So let's go and pop that on. Now notice the order in which I'm doing this. I'm not getting cracking at making scales or anything like that there. Right now what I'm doing is I'm labeling my x and y axes because they have marks. Okay, so we want resistance up the side, and that's going to be in, now we need a slash or a solidus, and then we need micro-ohms. Need the right symbols for that. There we go. So resistance in micro-ohms is going up the side. Turn that around. Probably need to shrink that a bit. At least you'll not be doing yours on computer. Okay, so pop that on the y-axis, going on there. And then on my x-axis, I'm going to want to have cross-sectional area. So down here, we want cross-sectional area. And then again we'll need a slash, and what was the unit for that? We'll flick back and have a little look. It was a millimeters squared. Now notice I'm not abbreviating, I'm not doing anything like that there, I'm not calling it CSA, I'm using exactly what they've used in the table, because why would you put yourself at risk? They use exactly what they used. Alright, so time to do some scaling. So cross-section area, we need to go from 0.08, and we need to take that across to 1.32. Okay, so I need to go from basically 0 up to about 1.4. Okay, so how many squares do I have to do that with? I have 1, 2, 3, 4, 5, 6, 7 squares to 1.4. That seems like it's kind of handy, because then we do 1.4 divided by 7, and that gives me each square is going to be worth 0.2. Okay, but I'm going to have to use the full width of the page to do that, so that's why we do our calculation first. And we'll go 0 here. Check that I'm putting the right one in here. Yep, for cross-sectional area. So 0 there, then 0.2 here, 0.4 here, 0.6, 0.8, 1.0, 1.2, and 1.4. Alright, I've come a little bit off the bottom here. That's probably a mistake, but we'll have a look. Resistance then needs to go down to 0.005, so essentially 0, and needs to go up to 0.1. So we've got 0.1 to get through. And how many squares do I have? I've left myself 1, 2, 3, 4 to there. That's hard to track. 5, 6, 7, 8, 9. Yeah, I knew that. I knew that. That's marvelous. Okay, well, this is a good opportunity for us to realize we made a bit of a mistake here. Is what we wanted to do, or what it's left us with, is we should be just basically running across the entire bottom. So we would ideally want that here. Now I can do that on the computer, no problem. But let's imagine that you're in an exam and you've done this. First thing to do, rub it out. If you've done it in pencil, but let's assume that we haven't. We've done it in pen. So we've got to do this. Okay, so we want it to go up in 0.1s or 0.01s. We can't really do that now. Okay, so 0.2 seems like the most obvious choice here, or 0.02 in this case. Okay, so start at 0 and go up in 0 and 0.02 jumps. Okay, so we'll roll my line up. Not ideal on this one, but we've got a resistance then is 0. Now, yeah, we could do like 0.015s and things like that, but that's just grim. You want to make a scale that you actually manage. So we're going to go 0.02. Now on 0.04, 0.06, 0.08, and 0.10. Okay, that's not ideal because look at how much graph paper we've wasted. But we're in this situation, we've done it in pen. We're probably going to lose our scaling mark. Maybe not, because we've used half the graph paper. But you want to really be using more than half the graph paper. Okay, so in this case, learning point here, draw this with pencil. That way if you need to move the line down one, it's better that way. Okay, well, we're stuck with this. Okay, let's go what we got. So now what you need to do is you need to plot the points. Now, if you've got to A level, you should be able to plot these points. Right, so we're not going to spend 15 minutes of you watching me plot points on a graph on a grid that's just horrible. Okay, but get your graph drawn, take your time at it. This is where your marks are though. There's 8 marks. Only about 3 of them are going to be for plotting the points. Maximum 3. Everything else is for this setup here. Alright, we've got a mark for this, a mark for this, maybe a mark for this scaling, a mark for this scaling, then a mark for it taking up half the graph paper, which we might not have got in this case, but you know, we'll take it. We'll take 7 out of 8. Next page it is. Okay, figure 2.1 shows the graph of length L of a spring and the mass M added to the spring. Okay, so we should be looking length of a spring, mass of a spring. So we're looking at Hooke's law here, but it's the length of the spring has caught my eye straight away. It's not the extension that we were expecting for Hooke's law. It's just the length of a spring. Right, and there it is. A, determine the original length of the spring. So the original length of the spring will happen when we had no mass added to it. So what we need to do is we need to extrapolate back our best fit line here. So we get a ruler, lay it along the best fit line, and just continue it back until it reaches here. Okay, mark the point off. Now you do this with a dotted line or something like that there. You know, do it kind of nice and subtly. So dotted line, bring down the thickness a little bit. There we go. Make it nice and accurate. Okay, so that looks like it's between 6 and 7. There's 1, 2, 3, 4, 5 squares. So every square is 0.2. So 6.2, 6.4, 6.6. Take your time. Don't panic. There's a lot of 6.3s would happen there. Okay, so pop it in, 6.6 centimeters. And that's our first actual bit of writing on a line in this paper. Draw an extreme fit line for the point shown on figure 2.1. Right, extreme fit lines are something that generally cause a little bit of a problem because extreme fit lines are like the worst possible line you could draw, but still plausible. Like the worst possible line I could draw for this is like, that's a best fit line, isn't it? You know, there. 3 on this side, 3 on that side. That's what you're taught about best fit lines, aren't you? Draw a line that's got as many points on one side as the other. But that's not the right answer here. Okay, the reason being that this is definitely wrong. Any idiot can see that. Okay, this is definitely the wrong line to draw. This does not represent the trend that's being shown in the graph. What an extreme fit line is you want a line that is just on the verge of being wrong. but is still right, or still could be argued to be right. So maybe something like that. Okay, that's pretty out there. In fact, I might argue that's all right. There. How about that? That's pretty extreme, isn't it? I've got 2 points below and 2 points above, but it's not quite right, is it? Anything this way, you bet. No, that's mental. Anything further this way, that's also mental. But there, it's a case of, do you know what? Yeah, maybe that's right. Now, the good thing about marking schemes is that if it's not ridiculously wrong, they're generally given. Okay, so the mark scheme is not going to say extreme fit line between here and here and here. If you're asked to do an extreme fit line, generally speaking, the marking is going to be, get a value consistent with your line. So I'm going to go with this, which gives me 5.8 as my intercept, but it only asks me to draw the extreme fit line. It doesn't ask me to do anything. And then determine the uncertainty in the original length of the spring. Okay, so the uncertainty here, we're looking for an absolute uncertainty because it's in centimeters. So the uncertainty is the error in your measurement. What is we've said it's 6.6 as if we're confident, but we've basically said that anything between 6.6 and 5.8 here is realistically possible. So what I'm really saying is that my answer is 6.6, but it could go down as low as 5.8. Okay, so that means that it's 6.6 plus or minus 0.8. Okay, because we have to go down negative 0.8. Now, in truth, we really should draw two extreme fit lines and go plus this, plus that, but we don't do that at AS level. We generally go with plus or minus the same number, because your extreme fit line should be, if it's extreme, then it should be just as extreme on the other side, because your perfect answer is perfect and should be bang in the middle. So that is my change in my y-axis value divided by my change in my x-axis value. So once again, go and grab our calculators. We do 1.36, take away 0.28, gets me 1.08 for my change in y, divided by my change in x, which is going to be 1.53 divided by, minus 1.75, which gives me negative 0.22. I need to be careful with that because this is definitely a downward sloping trend. Okay, so we definitely have a change that is negative. Okay, we have a negative change going on. It doesn't matter which way around you do it, you're definitely getting a negative change. So the gradient m is equal to, we've got 1.08 divided by negative 0.22, which gets me negative 4.90 recurring, so that's 91 to 2 decimal places. Okay, so that gives me my gradient. So negative 4.91 is what I'm after here. And my unit. So my unit is going to be my value of my y-axis divided by my value of my x-axis. So that is going to be amps divided by volts. Not enough to write the slash in this one, we have to put that in standard form, so that's AV to the minus 1. So amp volts to the minus 1. Okay, you could also have this as the volts over amps is an ohm, so it's the inverse of an ohm. You could have ohms to the minus 1, but keep it simple. Keep it simple, use the one that they've got, AV to the minus 1. And on we go. Part 2. Show how equation 3.1 can be mapped to the general equation for the straight line graph shown in figure 3.1. Yeah, we kind of knew this was coming. This is it's a straight line graph. It has the form y equals mx plus c. So you take this equation, E equals v plus IR, and you turn that into an equation that maps to this. Okay, so we need to compare this to y equals mx plus c. So E equals v plus IR is our equation. So we start with that. E equals v plus IR. Now the game is we need to get this in the form y equals mx plus c. So just write that up at the top just to remind ourselves what we're aiming for, that y equals mx plus c. And we need to have it that because our graph has the current on the y-axis, we need the current by itself out here, and we need the voltage over here with all the other gubbins with it. Okay, so the game is to isolate I in this case. Okay, so let's do that. So the easy thing to do first of all is to subtract v from both sides. Okay, it gets me E take v equals I little r. And then the only way we can now get rid of the little r on the right hand side of our equation is to divide through by r. So that gives me e minus v over r. That I'm going to divide each term individually. And the reason I'm doing that is to keep these things separate from each other, because y equals mx plus c has stuff separate. If I put it all over r, then it's never going to look like this. Okay, so I'm just going to divide it through like this. Okay, now just switch that around, because like I said, we want to have this in the form y equals mx plus c. We have then I equals minus v over r, following me, plus e over r. Now you don't have to turn it around like that. You could leave it like this and then do our mapping as we go. Now what you do then is you take the equation y equals mx plus c and write it below, and you just draw arrows. We have I by itself, so there it is. X is v. Okay, we've had that already. So m is minus 1 over r. Now we're going to need to write that out a little bit more clearly, because an examiner may not be able to follow that. Okay, so I is minus 1 over r times v. That looks a little bit better. Plus e over r. Now, let's manage this. So we want y is I, x is v, m is negative 1 over r. And it's probably a good idea to put some circles around stuff. So draw big. So we'll circle that off and make that circle just a little bit thinner. Okay, so x is that, and then c is all of this. And that looks cumbersome, but it's definitely a constant. Like E is the EMF of the battery, R is the internal resistance. Both of those are constants, so E over R is definitely a constant. That's how I knew to put it out there. So there we go. Alright, so determine a value for the internal resistance of the cell. So we need to find a little r. So that is a matter of finding the gradient. We've found the gradient already. So the gradient m is equal to negative 1 over r. We already have our gradient as negative 4.91. So negative 4.91 equals minus 1 over r. Okay, so the negatives go first, so 4.91 equals 1 over r. So r equals 1 over 4.91 equals 1 divided by 4.91. And we've got that it's 0.203. Okay, now internal resistance of the cell, 0.203 ohms. I'm going to go for 0.20 on this one because 3 decimal places seems like a little bit of overkill. Okay, and the reason it seems like a little bit of overkill is because I went 2 decimal places here on the actual calculation of m. The gradient itself is to 2 decimal places, so it seems unfair of me to try and do 3 decimal places for my value of r. Okay, 2 decimal places is probably around about right. There's almost certainly not a mark for it because there's only 2 marks here. It's unlikely that they're going to insist on significant figures or decimal places, but why not? Okay, explain how the EMF of the cell can be found from the graph. Now the temptation is to go up here and go find the y-intercept, then use E over r equals the y-intercept. Perfectly fine, except for the fact that our graph here does not allow us to do that. Okay, so I've extrapolated back this graph to here and gone, alright cool, my y-intercept is 1.52, except that it's not. Because the y-intercept is the value when x equals 0. And we don't have that. Okay, this is where x equals 1.5. Okay, now we can plug that into our formula. We now have a value for r and we can find that. But a far better way to do this is to extrapolate our graph onwards as I've done to the x-axis. Okay, and on the x-axis we have the current being 0 and the voltage being 1.81. And in this case, this is the internal resistance. Remember, the internal resistance, the EMF, try that again. This is the EMF, because the EMF is the potential difference that you have when you've got no current in your external circuit. It's the theoretical, before you plug anything in, voltage that's available to you. Okay, so in this case, rather than say, go through, find the y-intercept and use E over R to find that, what we actually have to do is, how can it be found from the graph? This is the key bit here. How would you use your graph to do this? We have to say, find the x-intercept. Because I equals 0 when V equals the EMF. Right? And that is that. 2 marks, so you could actually have to explain why you're finding the x-intercept. If it was 1 mark, it'd just be like, how do you find the EMF? Find the x-intercept. But it does say explain, so why is it that the x-intercept is useful? Because I equals 0 when V is the EMF. Okay, determine the value for the EMF of the cell. It's 1 mark, we read it straight from the graph, and like we said, it was 1.81. Just take you back and have a look at that. There it is there, 1.81, x-intercept. Okay, why should the experiment start with a variable resistor at a high resistance value rather than a low resistance value? Okay, immediately we're thinking low resistance, high current. High current means you damage stuff, you break stuff, you burn stuff out. So we start with, we go with low resistance, means high current, and high current increases risk of damage to equipment. Remember, the experimental setup here is just a variable resistor and a power pack. If you've got no resistance in that, you've essentially got a short circuit. You're just going to melt the wire. Okay, so we want to start with a high resistance and move our way down. Number 4. An experiment was carried out to investigate how the speed of a wave V traveling through water depends on the wavelength lambda of the wave. The time t for the wave to travel a distance of 5 meters, oh that's dirty, okay, was measured and the results were recorded in the table below. So the time for the wave to travel a distance of 5 meters. So we're going to be able to get the speed because we have a time and a distance. Alrighty. So we've got lambdas, we've got t's, we've got v's going on all over the place. I'm noting we've got 2 decimal places all the way down here. We've got 2 decimal places here. We've got a random 1 decimal place there. That's going to be interesting. And then over here we've got v's where we have 3 decimal places, 2 decimal places, but we've always got 3 significant figures. So I'm going to quickly just mark this as 2 decimal places, 2 decimal places maybe, and this is certainly 3 significant figures. Before I even start the question, these are things I'm noticing. May not come up, but worthwhile going. Got a relationship here, so we're almost certainly looking at a graph or a calculation coming along here. We've got k as a constant, we've got lambda, pi is obviously a constant, so is 2, and we've got v. Right, the same measuring device was used to measure all wavelength values. Explain why some of the values are coded to 2 significant figures, yet others are to 3 significant figures. Right, because when you're taking a measurement, we don't care about significant figures. We care about the accuracy of the equipment. So obviously our equipment is measuring to 2 decimal places. So this is the equipment accuracy. Get myself a black pen. Is to 2 decimal places. So this is the appropriate degree of accuracy. Okay, we're only going to bother with significant figures when we start processing results, when we start multiplying v's and lambdas together and we start losing some of our stuff. Okay, so that's fine. So this is the appropriate degree of accuracy regardless of size of measurement. So if I was measuring like 150 meters, it wouldn't matter because it'd be 150.00 because the equipment is able to measure to 2 decimal places. All the times were measured correctly using the same stop clock. One result has been recorded incorrectly. Write down how it should be recorded and explain your answer. So we've got our time and it's the 3.3. Do you remember we were having a little bit of panic about that? 3.3 is wrong. So 3.3 should be 3.30 because the stop clock could measure to 0.01 of a second. Okay, so you should confer your full accuracy in your results. Okay, so it's not about consistency or anything like that there. It's about being as accurate as you can be. When it's a straightforward, I took this result system. The speed of the wave for each wavelength except for 1.2 meters was calculated and recorded in the table. Calculate the speed for the wavelength at 1.2 meters. It gives us quite a lot of space for this one on 3 marks. So what are we after? Speed of the wavelength for 1.2. Okay, so the time t for the wave travel distance of 5 meters was measured, so I'm going to assume it's just meters per second. I don't see any problem with this, so we're going to go with 5 divided by 3.73. Again, maybe the 3 marks is for spotting that. So the 5 divided by 3.73, or maybe they want an equation. So we want speed equals distance over time. Always good to write your full working out, even at A level. So speed equals the distance of travel was 5 meters divided by the time it took it to do that, which was 3.72. There's too many marks here, so we're looking for the significant figures or the decimal places error here. So what we've got then is our speed, s equals 1 point, and then if you look in your calculator, it's 344086. Right, and this is what the test is, because there's too many marks available for just doing that. Okay, so we'll go back to our table, and we've got this. Each of these is to 3 significant figures, so we'll make sure that we quote our speed to 3 significant figures, and that's what it's after, 1.34 meters per second. Okay, what is the unit of the constant k? Ooh, a unit question. Excellent. So we've got to grab our equation. So v equals root k lambda over 2 pi. So v equals, well, let's pop back and see that again. Okay, so v equals root k lambda over 2 pi. So straight up, we want to square both sides of this because we need k. I don't really want to keep drawing that square root sign. So v squared equals then k lambda, and I'm going to switch back to just divide it by 2 pi. Now, when we're looking at units, then we only actually have to look at the things that have units. So 2 pi just immediately disappears. Has no bearing in this whatsoever because 2 pi is unitless. So now we've got v squared equals k lambda. So then we finally end up with v squared, switch it off symbol would be useful. The v squared divided by lambda is going to equal k. Okay, so what we need now is we need the unit for v, and the unit for v was the meter per second, so that's ms to the minus 1. And we want that squared, and then we want to divide that by the unit for lambda, which was meters, and that's going to be k. I'm just going to move this up here. Again, not luxury you have when you're doing your exam. So ms to the minus 1 squared is going to give me m squared seconds to the minus 2, and if you're not happy with that, write it out in full. So if you weren't happy with just seeing that, you do ms minus 1 and then again ms minus 1, because that's what squaring is. You've got 2 m's and 2 s minus 1, so you get m squared s to the minus 2, and then we've got to divide that by m, so over m, and the right font would be good, equals k. So that gives me that meters cancels with one of those, so you get ms to the minus 2. It's always comforting when you get something you recognize. Okay, so k, the unit for k is in meters per second squared. ms to the minus 2. 3 marks. Yay! So we're getting on well. Getting on well. And we're on to our final question. Okay, a basic experiment. Okay, so we're immediately looking at somewhere they're going to ask us to improve this. A basic experiment is performed to measure the acceleration of free fall. The only apparatus available is a ball bearing, a stop clock. Alright, cool. Well, as we're running through this, let's think about what we can get. So we've got a stop clock, a tape measure. The stop clock reads to 100th of a second, and a tape measure to the nearest centimetre. So we're going to have a time, and we're going to have a distance. We're going to be using our equations of motion, so we're going to use the equation of motion notation. And the stop clock reads to 100th of a second, and the tape measure to the nearest centimetre. Okay, so that's 0.01, and again 0.01 for the nearest centimetre as well, because we're going to measure these things in meters. Okay, explain how the results of a distance dropped and time taken can be used to obtain a value for the acceleration of free fall. Okay, now we will also know that we're dropping it from rest, so u equals 0, a equals question mark, s will be known, so that's good news, so s is known, and t is known. Okay, so we want s equals ut plus a half at squared is our equation for this one. But since u is 0, it's just s equals a half at squared. Alright, so we want to use s equals a half to at squared. So we want to rearrange that to give a equals 2s divided by t squared. So how can the results of distance dropped and time taken be used to obtain a value for the acceleration of free fall? What we want is to acceleration of free fall is 2 times distance dropped divided by the time squared, and just talk your way through it. Alright, happy? Ideally, though, what we want to do is, it does say how the results of distance drop, so this is how you would do it by calculation. My preference, though, and almost certainly the examiner's preference, would be to do y equals mx plus c, and it would be plot s against t squared for our graph. Then gradient would equal a half a, so a equals 2 times the gradient. And I'm imagining that's what we're after, because there's 3 marks there, isn't there? There's a mark for plotting s against t squared, there's a mark for the gradient being a half a, and then a mark for saying that the acceleration is twice the gradient. Job's a good one. Okay, so one for figuring that out, and then one for telling me what to do with it. In one experiment, the distance the ball bearing is dropped is measured at 1.95 meters, and the time of fall is 0.66 seconds. Calculate the percentage uncertainty in the measurement of the distance. Now up here, remember, we need to measure to the nearest centimeter, so we want a percentage uncertainty. So the actual uncertainty, so the actual measurement is equal to 1.95 meters, but it's plus or minus 0.01 because we're to the nearest centimeter. Okay, so we want to find the uncertainty in this. So the percentage, they're called uncertainty, so we're going to call it percentage u equals, and percentage uncertainty, just in general, is the size of my error divided by my measurement multiplied by 100%. Fill in my little equation there. Okay, so my percentage uncertainty, this font's a little bit too big, but that's okay, is 0.01, because that's the size of my error, divided by 1.95, and then we're going to multiply that by 100%. Stretch that out a bit, or lower my font size, probably a better idea. Apologies to the visually impaired that are watching. Which gives me a percentage uncertainty equal to 0.01 in your calculator divided by 1.95 and then multiplied by 100 gives you a percentage uncertainty of 0.51%. So that's pretty good. So percentage uncertainty equals 0.51. So you want 0.51%. Grand job. Okay, so assume the percentage uncertainty in the time of fall to be 8%. Calculate the absolute uncertainty in the value of the acceleration of free fall. So what we want to do here is we're going to need to find the total percentage error, and then we're going to need to find what that percentage is of the actual value of A. So we need to actually find A to start with. So A equals 2s over t squared. Okay, or s equals ut plus a half at squared, and work it through to get this. So A equals 2 times, I think it was 1.95, we'll go back and check that in a second, divided by 0.66 squared. Just to check that was 1.95. I'm pretty sure it was. We'll just check it. Yeah, 1.95 meters. Okay, so 1.95, 2 times 1.95 squared divided by 0.66, get squared. Pop that into your calculator. Take no chances, and we get A is equal to 8.95. So the percentage uncertainty in A is going to equal the percentage uncertainty in S. Okay, so we'll just put percentage uncertainty in here, percentage uncertainty in A. It's the percentage uncertainty in S. Yes, it's multiplied by 2, but that's a set number. So we don't double the percentage uncertainty here, we just keep it as a regular percentage uncertainty, because if it's twice that, the percentage takes that into account. We're going to then have to add on 2 times the percentage uncertainty in T, because it's T multiplied by T, so the percentage uncertainties get added. Now I imagine there's going to be a couple of questions about this bit here, but think about it. If I have a value of 50 and the percentage uncertainty is 10%, right? So the actual uncertainty is 5. Following me? Then if I double that value, my value becomes 50 goes to 100, but the percentage uncertainty still remains at 10%. At 10. Okay, if that's not clear, we'll maybe clear that up in the live stream a little bit later on. Okay, so the percentage uncertainty in A is equal to my percentage uncertainty in S, which we just found back here, which is 0.51, plus 2 times the percentage uncertainty in T, so that's 2/8, which is 16. So my percentage uncertainty in A is equal to 16.51%. Yes, we're doing well. So now what we can write is that A is equal to 8.95 plus or minus 16.51%. But we want an absolute uncertainty, not a regular uncertainty. So we need to go and find what is 16.51% of 8.95. So we want 8.95 divided by 100, which gives us what 1% is, and then we want to multiply that, mind my bid mass, multiply that by 16.51. And that gives me 8.95 over 100, then times by 16.51 on our calculator, gives me 1.48 to a couple of decimal places. So then A equals, we're not asked to do this, but it's nice, 8.95 plus or minus 1.48. And that puts 9.81 nicely within that bracket, so that's good news. And the absolute uncertainty, 1.48, is what we're looking for here. Alright, on we go then. Find the percentage difference in the experimental value of acceleration of free fall compared to the accepted value of 9.81. So find the percentage difference in the experimental value of acceleration. Right, okay, cool. So we go back and we go, right, we had our experimental value A, and it was equal to 8.95. So A equals 8.95. Okay, and we want the percentage error is equal to the actual error, or the difference, over the accepted value. And we'll want to times that by 100%, but we'll not clutter things up a bit. I know, we'll be specific. Times 100%. Okay, now my actual error is, well, I happen to know what the accepted value is, so all I need to do is go 9.81 minus 8.95, that's the actual error, divided by my accepted value, which is 9.81. Stick a line in there to show that's a fraction, and then we times that by 100%. And again, back to your calculator you go, 9.81 minus 8.95 divided by 9.81, and then times 100% again, or times just 100 on your calculator, and that gets you a value of 8.77%. Somewhere around about 9%. Right, and then finally, suggest ways that we could adapt this experiment to give a result closer to the expected value. I was getting worried there that it wasn't coming up because the word basic was in there, but we knew this was coming. So how do we adapt this result to get a value closer? Right, first of all then, we want to repeat the experiment to get more reliable averages or average values. Right, that's stage one, okay, because we've done this entire calculation with one value. Okay, if I could spell experiment, that would help. There we go. Now, so repeat the experiment to get more reliable average values. Now we're going to talk about the equipment here. We were timing it, remember, with a ruler because it said basic and a stop clock. So what we want to do is we want to use light gates or automatic timers of some description. And then finally, you didn't do it this way. You did not do this experiment ever using calculation stuff, because we want to establish the acceleration graphically using the gradient of, remember back at the start of this question, using the gradient of an s against t squared graph. All comes together. Okay, I hope this has been vaguely useful to you. Hit the like button. I know this is a long video on this one. Hit the like button if you liked it. Hit the dislike button if you didn't. That's fair enough. And if there's anything that you'd like me to go over later on this evening on the live stream, please drop a comment below. If I don't get any comments, it looks like I'm having a free evening, but I'll maybe pop on and wish you all the very best. All right. Work hard. All the very best of luck. And don't forget, everybody, physics rocks. It's true.